Good afternoon. Let's start. So my name is Qazi Hassan. I will be lecturing first part of this course, first 6 weeks. And last week, for some RMIT teaching responsibility, I was in Hong Kong, so I was not here. I think you met Dr. Nuantha. And you have the course introduction. So in first half of the course, we will be going through single-phase circuits, what we have done last week. Then this week, we will go through three-phase AC circuits. Then we will review the magnetic circuits, single-phase transformers, three-phase transformers, and DC machine. So that will end in the first half of the semester. Then in the second half of the semester, Dr. Nuantha will teach synchronous machine and induction machines. So now to start with three-phase AC circuits, there are actually 4 components in today's lecture. So 4 types of studies or 4 parts in this lecture. And you will see in your tutorial 4 types of mathematical problems. So firstly, we will go through the three-phase instantaneous power calculation, because in single phase we have seen that power, real power P equal VI cos theta. That will not be true in case of three-phase power. So we will derive the mathematical power equation for that three-phase power. And in the second part, when there is three-phase in a circuit, in a systems, those three-phase can be connected or arranged mainly in 2 different ways. One is called Y connection or star connection, another one is delta connection. So we will go through that aspect as well, that how do we calculate phase voltages and currents, line voltages and currents in delta connected circuits, in Y connected circuits. And how do you calculate power as well from a delta circuit and from a Y circuit. So we will revise that or learn those in the second part of the lecture. In the third part, we have learned maybe in some other courses power factor improvement, but in this course we will do that for three-phase circuit, because there are many realistic power circuits which are actually three-phase. All high voltage circuits are three-phase. So how do we do power factor improvement in three-phase circuits? And in the fourth part, we will learn about the tools and techniques to measure power. I'm sure you have measured power in your labs, maybe using wattmeter. So what is the construction of a wattmeter? How do we measure? What is the measuring principle or working principle of a wattmeter? So these 4 sections we will cover today in our lecture. We will try to solve problems, mathematical problems in the class in each of these topics. And again, in your tutorial, you will have mathematical problems on each of these topics. So let's start with three-phase circuits. So this is a three-phase generator, and this is a three-phase load. And as you see the connections, these connections, there is just one common point among all of these, and it looks like a Y, so it is called Y connection or star connection. And that looks like delta, so that is called a delta connection. So in three-phase circuits, the connection can be either of these 2 types. There is a word said balanced. When we say balanced, it means that the voltage VA, VB, VC, their magnitude is equal. So their amplitude, their value is equal. The phase definitely will be different. And then in this part, when we say balanced, all of the impedances you see Z, that will be equal. That's why we call it a balanced circuit. And if the value of Z is not equal, then it will create an imbalanced circuit. So if you study some advanced course in power systems, advanced power system analysis or some other course, you will see that the mathematical equation for power calculation and some other power system studies like fault analysis, balanced system and unbalanced system is totally different. So the theory we can apply to balanced system, that is not true for unbalanced system. So that's why at this moment I want to emphasize the term balanced. And in this course we will only cover balanced system. It means all of the three phases are the same. In our real life, in reality, what happens that, as we said, that the high voltage system is three-phase, but when it comes to our home, we are in single phases. So when they give connection in a distribution feeder, three single phases, so consider your street, maybe all of the houses connected in one phase, phase A, your neighboring street in phase B, and another street in phase C. So what happens, definitely all of these streets are not consuming the same amount of power. So it means the system is unbalanced. But the calculation gets very complicated. So first we try to learn and start with balanced system, but in reality the system is not balanced actually. Maybe unbalanced. So if you study some other course, you will learn that. But we will consider balanced system here. Now, that is Y connection and this is delta connection. And what we see here, these are the lines, three lines. So if you look at on your left at point C, A or B, you can see that the lines are going from Y to delta. So these are we called line, and each of these is known as phase. So in Y, if you look at VA, the current is flowing through this phase towards point A. The same current is going through the line. So for Y connection, phase current is same as like line current. But if you think about delta, in delta the phases are like this, phase A, B and C. The line current which comes here, that is not equal to the phase current because it divides into two phases. So when we do the calculation, we have to remember that for Y connection, star connection, line current and phase current is same. But for delta, line current and phase current is not the same. On the other hand, if we look at our Y, our phase voltage is VA. And when we call our line voltage, sometimes it is referred as line to line voltage. So line to line voltage means voltage between point A and B. As you can see, the voltage between point A and B is not the same as VA. So in Y connection, the phase voltage VA is not equal to line or line to line voltage VAB. If you look at your delta, the phase voltage is across point A and C, and line to line voltage between A and C. So whatever you see your phase voltage in delta circuit, that is the same as line to line voltage. So we have to remember these four combinations. In Y connected circuit, phase current is same as line current. But phase voltage is not as line voltage. In delta, phase current is not as line current, but phase voltage is same as line voltage. So in Y, line current equal phase current, but phase voltage is not line voltage. In delta, line current not phase current, but line voltage is phase voltage. In most of the calculations in three-phase circuits, we need to remember this. So I would encourage you to put this into your memory, into your brain. Because most of the mistakes usually students make in the exam just for this simple calculation or assumption. So for Y, line current is same as phase current. For delta, line voltage is same as phase voltage. Here, phase voltage is not equal to line voltage. So what is that? It is not equal, it is unequal, but what is the value for that? We will derive that. Okay, now phase voltages. I think you have some basics about three-phase systems. There are three phases, phase A, B, and C. And because the full circle, the sine wave from which generators the power is coming, the maximum angle would be 360 degrees. And three voltage, they stay apart equally. And the phase difference between each of the phases is 120 in balanced systems. So if you think your phase A is reference VA voltage, and phase B, that will be 120 degree lagging, so minus 120 degree, and that is minus 240 degree or plus 120 degree. So VA, VB, VC, three signals in three-phase systems. So if we consider our voltage VA, that is the reference, so the angle will be VA 0. In case of VB, with respect to VA, that is minus 120 degree. And our VC, with respect to VA, that is minus 240 degree. But you can write it another way as well, plus 240 and plus 120. So the phases is 120 degree apart from each other by themselves. So these are phase voltages, VA, VB, VC, and they have 120 degree phase shift. So these are balanced phase voltages. Now, we said that, for example, for Y connected circuits, phase voltage is not as line voltages. So what is the relationship between phase and line voltages? As we have said, that our VA is 120 degree apart from VB. So VA is one phase voltage for phase A. VB is another phase voltage, phase B. They have 120 degree phase shift in between them. Now we want to calculate the line to line voltage between VA and VB. So the line to line voltage will be VAB. And we are doing vector summation here. So how do we get VAB? VAB is VA minus VB. So the blue line here, it shows VAB. And we put the value of VA, that is a phase voltage. Angle is 0. Again VB, another phase voltage. Angle is minus 120 degree. Now we need to subtract VB from VA. So subtraction we cannot do in polar form, so we convert them into rectangular form. Then once we do the calculation, we see that our VAB, it gives us the value root 3 VP, means V phase, and there is an angle 30 degree. VAB, line to line voltage or line voltage in Y connected circuits or star circuit, and VP is the phase voltage. So this equation shows the relationship between line to line voltage and phase voltage in a Y connected circuit. And that is for phase A and B. If we do the same calculation, similarly we will find the same equations for BC line to line and CA line to line. So what we have in these equations on the left side, line to line voltage or line voltage. On the right side, phase voltage. So we can come up with this conclusion, and it is very important to remember this. The line to line voltage of Y connected source is √3 times higher than the phase voltage. So VL equal √3 V phase. So line to line voltage √3 times higher than the phase voltage. And there is an angle of 30 degree. So if we draw all of the three phase and line voltages, it will produce a vector diagram like this. That you have VA minus 20 degree apart VB minus 240 degree apart VC. Then your VAB will be 30 degree, but the value is √3 times more. So in Y connected circuits, line voltages are higher than the phase voltages. So this is the relationship between phase and line voltages in Y connected circuits. What is the relationship between line and phase current in Y connected circuits? Same, they are equal. So now we go to the power calculation for three-phase circuits. Is there any question up to this point? So now in the power calculation, we are taking Y connected circuits. It is showing three phases and line currents. So just we are considering a voltage VA, that is √2 VA sine omega t, and VA is phase voltage. So we write √2 V phi sine omega t. Now the current, if there is some impedance and some angle, the current angle will be different. So the current will be √2 Ia sine omega t plus theta. So theta is the phase angle between voltage and current. So this is standard form. If you start by saying that I want to use cos function, that is fine as well. So it doesn't have to be √2 Vp sine omega t. It can be cos omega t. So now we have voltage and current, and both are phase voltages and phase current. For Y connected, phase current and line current is the same, but phase voltage and line voltage is not the same. So we will consider that later. Now if we want to calculate the power for each of the phases, so this is phase A. The power will be P equal VI, voltage of phase A, current of phase A, and it will give you, once we multiply with voltage and current, we get 2 V phi I phi sine omega t plus sine omega t plus theta. So this is the phase voltage for phase A. And from here, because it is 2 sine A sine B, there is a formula like we can write cos A minus B minus cos A plus B. By using trigonometric formula, for phase A, we got this quantity, V phi I phi cos theta minus V phi I phi cos 2 omega t plus theta. So this is the power calculated for phase A. Now phase A power is this one. I'm going, so if you cannot copy this, don't worry, I will upload this slide in Canvas, and that will happen by the end of the day. So you will get these slides today. For phase B, similarly we calculate the power, and that gives us 2 V phi I phi sine omega t minus 120 degree. For phase C, we calculate that again. Now the total power will be, because this is a 3-phase system, first we calculated the power for each of the phases. Now we add all of them together. So it gives us PA plus PB plus PC. So once we add all of them together, the total power we get P equal 3 V phi I phi cos theta. There is no surprise, because for single phase power was Vi cos theta. For 3-phase you just multiply with 3, because all are balanced, it means all are same and similar, so the power will be 3 V phi I phi cos theta. So this is phase V phi I phi, and this is Y circuit. So I phi is same as I line, but V phi is not. So phase voltage is not a line voltage. So if we want to represent in terms of line to line voltages, then it will be √3 VL IL cos theta. So when you apply this formula in your calculation, remember that which equations you are writing, which parameters you are considering. Power calculation can be done by 3 VI cos theta or √3 VI cos theta. So is it 3 or √3? That will depend on your voltage and current, whether you are using phase parameters or line parameters. Many students make mistakes many times with these 3. So 3 and √3, but which one to use? So just remember, be a bit careful about this, which equation you are using. Maybe you write 3, but you use line quantities. Or you write √3, but you use phase quantities. So be a bit careful about this. So in terms of line to line voltages, our power equation is √3 VL IL cos theta. And similarly, if we consider like our reactive power, if that is cos theta, this will be sin theta, here the same. So your reactive power will be √3 VL IL sin theta. And the apparent power S, that will be √3 VL IL for this. So real power, reactive power, and apparent power, all of the equation will be in this form in terms of line to line quantities. So this is what, from where we started, a balanced system, Y and delta, relationship between phase and line voltages and currents, and calculation of power for a 3-phase system. Now, just a bit review of this. Voltage and current in a Y circuit. So what happens in case of line voltage? Line to line, A to B, that is not as VA. That is √3 times of VA, but current is the same. Power, √3 VL IL cos theta, reactive power sin theta, apparent power √3 VL IL. So these slides are just for your revision. So you can go through quickly before your exam where you see all of the formula is there. Then for delta connected circuit, IL, the line current which is coming to A, that is not the phase current. So that is root 3 times of phase current. But voltage between phase A and B is the same in this phase. So VL is same as V phi. Power, if we derive the equation, we will get the same, root 3 VLIL cos theta, root 3 VLIL sin theta, and the apparent power. So this is the comparison, all same, just on the top, phase voltage and phase current are different. Now let's solve a problem. On 3-phase circuits, delta Y connected circuits. 415 volt 3-phase system supplies 12 kilowatt at a power factor of 0.9 lagging to a delta connected load. So the load is a delta connected load. It is a 3-phase system, delta connected load, 12 kilowatt, power factor 0.9 lagging. So this is the information given. Determine the line currents, phase currents, and phase impedance of the load. So from where do we start? So what do we do with this? First we write all of the quantities which are given. For example, V, because it is a delta connected circuit, it is saying that at the end. So what is 415 volt? Is it phase voltage or line voltage? Again, a bit loudly please. This is phase voltage. What will be line voltage if it is a delta connected circuit? So this is delta connected circuit. It is saying that 450 volt is the voltage given, but it doesn't say whether it is phase or line. It is a delta connected circuit like this. And it is saying that 450 volt is the voltage, 415. And if you are saying it is phase voltage, okay, I trust you. But what is the line voltage? A bit loudly, please. Same, isn't it? Yeah. So don't get confused. That's why I am spending much time to go through this again and again, that just imagine a delta connected circuit. If this is phase voltage across this is the phase, and the voltage drop here is the same as voltage drop between A and B. So in delta connected circuits, phase voltage will be the same as line voltage. So they are no different. This is the same. So when you see these numbers and you try to convert 415 by multiplying with root 3, you are gone, isn't it? Because it is the same. So you don't need to multiply with root 3 and make it into line voltage, because in delta connected circuits, phase voltage and line voltage is the same. So you write that this is the line voltage or phase voltage. It is the same. And the value of P, power is given 12 kilowatt. So what is given in this? VL, line voltage 415 volt is given. P, power 12 kilowatt is given. Cos theta, power factor is given 0.9. What we need? We need we need to get line currents. So we know VL, we know P, we know cos theta. So let's go back a little bit. If you look at P in this equation, we know P, we know VL, we know cos theta. We need to determine IL from this equation. Is it difficult? It is not difficult because all of the parameters are given. We know that P equal root 3 VL IL cos theta. The value of P is given, value of VL is given, and cos theta is given. So look at the question again. 415 volt, 3-phase system supplies 12 kilowatt power, lagging power factor 0.9, delta connected load. Delta connected load means phase voltage time line voltage is the same. So that is VL given, P given, cos theta given. We need to determine IL first. So you just write simply this equation. Line current IL will be P over root 3 VL cos theta. The value of P is given, VL is given, cos theta is given. Then it was asking for phase currents. This is a delta connected circuit. This is a delta connected circuit. So the line current goes and it divides into two phases. So line current and phase current is not the same. So how do we determine the phase current? So we go back to the relationship between line current and phase current of a delta connected circuit. So that's why I have given this slide to you. So that in a delta connected circuit, line current and phase current, that is the relationship. So if you need to determine the phase current, that will be line current over root 3. So once we know the line current, here we can determine the phase current by dividing with root 3. So we have the line current, we have the phase current. Now it was asking for the phase impedance. Impedance per phase for each phase or single phase. So how do we get the phase for each of these phases? We get the impedance by dividing the voltage with the current. So V over I, that will be the impedance. Because it is phase impedance, so that will be V phase divided by I phase. Because it is delta, V doesn't make that much difference. V is the same, whether it is V phase or VL. So the voltage will be 415, but we will use I phase to calculate the impedance. Because it is asking in the question that determine the phase impedance. So we calculate the impedance for each of the phase, and that is phase voltage divided by phase current. It doesn't matter whether you write is line voltage or phase voltage, because it is the same. That is 415, but we use the phase current because impedance is in each of the phases in delta. And we calculate the angle from the given power factor. If you have any question, confusion, you can ask me now. So you can see that when we are doing these calculations, we need to use our imagination of Y and delta circuits and then use the formula. So it is not straightforward. You have to understand the circuit, that how the elements are connected in delta and Y, and what is the voltage and current relationship between those. Yes.
So for the Y connection,
Yes.
there are two ways to find the P power. One is using the phase and one is in the line. So in here you're using the current in the phase to find the current in the line. So can I use the formula?
Are you looking at this problem?
Yes, still.
And you are saying
For the
why
phase,
you
for
are,
the I phase.
no, you are saying Y connection, or
It's like we have two formulas for the power.
yeah,
So we using this one.
the formula we are deriving,
Yeah. So can I use this formula to find the current in phase?
the formula we have derived, we have shown,
Yeah.
that was for Y connected circuits.
Yeah.
And this problem
It's of that.
is a delta connected circuit.
I thought like they use the same formula for the current.
Yeah. At the end, the formula is same.
Yep.
Yeah. Now what is your question?
Because
P equal √3 VL IL cos theta. Yeah, sure. Yep. This phase current? Yeah. If in this phase current, we can determine the angle from the power factor at the beginning, then we can put the angle there. So if you are not asked to calculate that, so you don't need to give. But if you are asked, then you have to give the angle there. Is that okay? Can we proceed? So this is three-phase delta connected circuits and the calculation of power, line current, phase current, and impedance. So these Y and delta connected circuits, just a little bit of refreshment, like background information, why we are using these. So we have done some mathematics, and we have seen by now that all of the Y connected circuits, there is a neutral or common point in all of the phases, but in delta there is no neutral point or connection. So these are just for your general understanding and review about Y connected and delta connected circuits. In Y connected circuits, though it is three-phase, there can be 4 wire systems. How it works? It works like this. If we go one of the Y connected circuits, for example here, there are 3 wires, A, B, and C. Maybe you see that there is another wire is going from neutral. So sometimes there is a neutral connection in Y. The circuit arrangement could be like this, different. Because this is very high voltage, so it needs some grounding, so sometimes they ground it here. So in Y connected circuits, that can be 3 wire system like this, or there can be one connection, like 4 wire system. But in delta, it is always 3 wire system, because there is no common point in here. This is just some general information about when we compare these 2 systems together. So I have given some comparison between these 2. As you have seen already that phase voltage and line voltage, there are some issues, but the power calculation is the same. The speed of Y-connected, star-connected motors are a bit slower because in each of the phases, the voltage is less than delta. Because delta, the phase voltage is equal to line voltage, but here phase voltage is lower, so each of the phase gets lower voltage. If you connect a motor in each of the phases, they get smaller speed or lower speed. Because of the low voltage in each of the phase, low insulation is required. Lower insulation is required. That's why they use mostly in very high voltage systems. And there is an advantage of using ground or neutral wire. So in very high voltage, in transmission system, they mostly use Y-connected circuits. In distribution, delta-connected circuit is popular. So these are just some comparison. Now, if it is a balanced three-phase circuit, if all are same, phase A, phase B, phase C, then as you can see that when three phases are coming, the calculation is getting a bit complicated. So if they are balanced and you want to just do simple calculation of, it is called per phase calculation. So you can convert your equivalent per phase circuit. So this is a three-phase circuit and there is a neutral wire connected there. If you solve this circuit for phase A, that will be true for other phases as well because all are balanced and all are the same. So sometimes three-phase system is represented in per phase equivalent circuit like this, and this is nothing but what we have seen in our single-phase system. So three-phase system can be studied as a single-phase system as well, provided that that is balanced. So from this connection, YY, if it is YY, you can get an equivalent per phase like this. Again, from YY connection, you can get equivalent per phase single-phase circuit. Y. So you get this circuit. If it is Y delta, what will be the single-phase circuit? Try at home. Okay, now, so we have seen that this is actually the relationship between phase voltage and line voltage, √3, and there is an angle of 30 degrees. We have derived that before. So balanced line voltages. What happens to delta currents? Because we have derived here, this is Y-connected circuit, line current, phase current, same. Line voltage, phase voltage, not the same. This is the relationship. So this is for your review again. And this is again for your revision that in delta, phase voltage, line voltage is the same. Phase current, line current, not the same. This is the relationship. Am I repeating the same stuff again and again? Let's do a calculation. So this is a bit complicated, but a bit interesting as well. This problem, this mathematical problem, I would say that one of the most important or prominent types of problems in this course. Because each course is designed to develop some of the skills for the students. So in this course, we wanted to develop the skills for Y delta parallel connection of the circuits. So this is one of the very good example of this course that what we want you to be very comfortable with. So what you see here, there is a star connected load, it means Y connected load, and a delta connected load. And they are both connected in parallel. And they are not alone. There is one source connected to that as well. So there is no blackboard in this room, is it? And we can't write on this, isn't it? Is there any no solution? There was one. Okay, that's fine. Maybe next time we will arrange something. Yes. Okay, good. That can be part of the solution. Part of the solution. So what do? You go to the document. It is good. We are going dust free. Now what it is said that there is a Y connected circuit. Can you see it? No, only I can see it. It is better. So what it is saying that there is a Y connected circuit and there is a delta connected circuit. So they are connected like this. That's what it is said. And then the value here 2 plus J3 for each of these. And then 6 plus J6. 6 plus J6. So they are connected in parallel. When you see this connection, I just wanted to make sure that phase A is connected to phase A, B with B, C with C. That's why we make like this. And the other point is that they are connected to a source. So it is connected with a source. And when we say source, those are generator is usually connected in a Y connection. So this is the generator. And when it says 400 volt generator supply, it means actually line to line. So this was our circuit. Two loads are connected in parallel with a generator. This is a 400 volt 50 hertz supply. Now what you see here, this is a Y delta connection. So there are some problems in your tutorials or maybe in your study materials which are doing Y connection, delta Y, delta delta, and you see there is no impedance in between this line, then in some questions, impedance will be added here. So whatever problems you find of this type, please try to solve all of those. So now in this connection, what we need to determine? They are asking to calculate the line current supplied to each of the load. So line current supplied to each of the load means we need to calculate the line current for Y connected circuit and line current for delta connected circuit. And then overall supply line current, it means the total current going from here. Then the total power drawn from the source. So it means whatever the power is consumed by these two loads. Then overall power factor. So we have to determine the line current for each of these circuits. Then total line current, total power, and total power factor. So what is given here, because we need to know this line current, what is given here is the voltage and the impedance. So we know the voltage between these two terminals. We know the line-to-line voltage. And we know the phase impedance. Now we need to calculate this current IL. Now if I write an equation, IL equal V over Z. I want to write Z phase, means Z only for this phase. If I want to get the current in this by calculating this impedance, which voltage should I consider? Is the voltage between here or the total voltage? Because I am using the impedance only this part, so I am considering the phase voltage. And our phase voltage will be line to line voltage 400 divided by root 3, and again divided by our phase impedance, that is actually 2 square plus 3 square. If you don't understand, please ask me questions. It is very important to understand this type of problems. For this course, you want to make sure that everyone understands this type of problems. So it was asking to determine the line current. So we have calculated the line current, but that is for this circuit, for Y. Then what is the power, real power consumed by this part of the circuit? So this part of the circuit, each phase, the power loss will be I square R. Here the power loss will be I square multiplied by this R. Because all are balanced and there are 3 phases, total power loss here will be 3I square R. And in this case, what I we will use? It doesn't matter actually, because it is the same, phase and line in case of Y. 3 I phase square R is actually 2. And I phase will be whatever we get here, we divide with root 2. Yes or no? We get our line-to-line current. Is that different from the phase current, what we want to consider here? They are same, because this is Y-connected circuits. Say it again. Time 3. This one? This is the value of R, the resistance. Because it is real power, so that will be the power consumed in the resistance. If it is reactive power, that will be the power consumed by the inductance. Is that okay? P is I square R, this is R, and Q is I square X. So, if we look at the complete solution, so firstly, this was the question that balanced, So balanced star was connected with balanced delta. Then it was asking to determine the line current, then power and all of those. So the first step we have done, that because we need to determine the line current, to calculate the current, voltage is given, so we need to determine the impedance. So we have calculated the impedance, then the line current is phase voltage divided by the impedance. Phase voltage 400 over root 3, and the impedance we calculated there. So this is our line current. Star means Y-connected circuits. Then we calculate the real power, that is 3 I square R. We use the value of I phase because that is the same as I line. In Y, phase and line are the same. And we multiply with 2 here because of this resistance value in the impedance. And when we calculate Q, this 3 is coming from this X. If you are unsure about any of these quantities, please ask. So this was for our Y-connected circuits. So we have done actually the calculation only for Y part. Then we have to do the calculation for delta part. For delta connected circuits, impedance was given 6 plus J6. Then to calculate the current, and this is line current. So we have divide the voltage with the impedance. So the voltage 400 volt, that is the phase voltage in each of the phases. And the impedance 8.49, that is each of the phases. So the current you get here, 400 volt divided by this. So this part of the current is phase current. That's why we multiply with root 3 to make that as line current because this is delta connected circuit. Just give me a second. Remain with me. What I mean by here, as you see, 400 volt is here within the phases. So between phase A and phase B, you have 400 volt. When you divide your 400 volt with this impedance, the current you get, that is actually I phase for this phase, because you use the voltage here and impedance here. So you get the current here. This is phase current. So to calculate the line current, you need to multiply with √3. Is that okay? So that's why when you look at the solution, you see a multiplication with √3. Then now the power calculation, what happens to the power? We calculate the power with the equation I square R. And why 3 is there? Because we consider 3 phases. So it means this power is for per phase. Per phase means this current is phase current. So the current you calculated 81.65, that was line current for delta. For delta, phase current will be 81.65 divided by √3. Then when you square it, that's why you see a 3 here. Is that okay? 3 I phase square R, and I phase is I line 81.65 divided by √3. When we square it, that becomes 81.65 square divided by 3. So the current we consider here is the phase current, and similarly reactive power for your delta connected load. Now, what is the total real power? Real power loss in these 2 circuits, because there are 2 circuits, delta and Y. So, Y connected circuit consumes 24.61 kilowatt power, and then delta connected circuit consumes 40 kilowatt. So, the total power consumed by these 2 loads are 64.61 kilowatt. Total reactive power consumed is just add Q delta and Q star. That gives us 76.92. So that is the total power loss in the circuit. Then we calculate the total apparent power, S, that is root over P square plus Q square. To calculate I line, so this is S equal √3 VLIL. S equal √3 VLIL. So this is the way we calculate our line current. And this line current is the total line current coming from the source, because this is the total apparent power coming for 2 of the loads, for Y and for delta. power factor that is coming from your Q divided by P. And these relationships, these are coming from the power triangle. The relationship between real power, reactive power, power factor, and apparent power. Have you studied power triangle in some of the courses? Power triangle, yes, okay. Yeah, that's it for this problem. It is a bit lengthy, little bit complicated, but in this course you will have this type of problems. You have to solve many of these. So there will be y delta, delta y, delta delta, line impedance between them, or there is no line impedance, so there will be a lot of combinations of this type of circuits. Any confusion about any of these numbers, please ask me. If you are very much confident about this and this type of circuits, that is good for this course. Yes?
For that last line current, what current is that? That last one that's 145 amps.
This is the total current. So this is the current that is going from this source. So what we calculated, we have calculated total Py for these three and P delta for these three, and subsequently Qy, Q delta. Then we have calculated Sy, S delta. Then we add them together. So the current, what we calculated here, that was from S total and VL, which is this V. So that's why this current will be going from the source, which is the total current. So this current we have calculated from the total S. You can see 100K from this. So the current is the source current. And in the question it was asked actually, the overall supply line current. So it is the overall supply line current from here. And the total power, that's why we calculated individual power, then add them together. And the power factor we have calculated from the total S, total P, total Q, that's why that is total power factor, overall power factor. Any more question, please? All good? If you are happy, then I think we deserve a 5 minutes break, isn't it? Can we have a break for 5 minutes? Yeah.
Clearly stuff in a few of my classes. Instead of like textbooks for each of them, is there like one good textbook to do these problems?
For mathematical problems,
Just for like these
this type
star
of
delta and all that sort of stuff.
following any textbook will be fine.
Yeah.
Any of them should be fine, but I think we have recommended which one? Gildy?
Yeah.
Yeah, that is one. So I think that is from Pearson's publications. So yes, if you just follow any standard textbook, that will do the job. Just in some cases, you may get confused about the notation, because some say VA or other will say VAN to represent the phase voltages, or maybe some will represent in a different notation. But conceptually, I think if you just follow one and stick to that, that will be good.
So just double checking with the it's either times by root 3 or times by 1 over root 3. So because in this case it's times by 1 over root 3 because the supply is set in a Y connection.
No, it doesn't matter. It doesn't matter. Your S is always root 3 VLIN, irrespective of Y or delta.
Oh, okay. So then why?
Because I am calculating IL.
Oh, I see. Yeah.
So this root 3 is not for Y delta. This
Oh,
root 3
okay.
is for
So that's where this came from. It came from deriving. Oh, okay. I get it. Thank you.
So we're just a bit confused on this formula.
good. It is good to be confused. Then there is some scopes to discuss, isn't it? Very good.
So we're just not sure why you use 3 instead of square root 3.
And divides by.
Oh, wow. That's very interesting. This is for delta, isn't it? So in delta, you are like this. And you are like this. And then what you want to do, you want to calculate the total power. So we are calculating total power. Power is, so for example, if I have R plus Jx here, then how do I calculate the power here? I calculate the power here by I square R. That is the power loss. Okay? And from where? So the I is flowing through this, isn't it? What I is this? Because this was the line, isn't it?
I phase.
So that is actually I phase. So this is IP, okay? So now, what I want to do, I want to calculate the power I square R, and this is actually IP square R, because this is the phase current.
It's only one, each one.
Only one. So what I want to do for the whole circuit?
Times 3.
I want to write 3 IP square R. Am I right?
Yeah.
Good. If this is my I line and this is my IP, so what is my IP? The relationship between my IP and IL. Our IP equal IL over root 3, isn't it? Or IL equal root 3 IP. I mean, the way you want to say it. So the IL, this one we calculated, this was line, but here, so we want to write IL over root 3 just from here and square over R. Do you agree? Or not?
Oh, square. He's take out the square root. Yeah.
So this 3 is coming from there.
That's why we confused why we put the 3 in this place.
I think I just figured it out when that root rate goes from. The same thing.
This one? This one?
Yeah, that root rate.
This root 3 is coming from. So this is S, isn't it?
Yeah.
You understand? Because that's what just recalculated. And this is our IL here, isn't it?
Yeah.
And this is root 3. And what is this actually? This is VL.
That's VL, yeah.
VL. That's it, isn't it? So that's what we have written here, isn't it?
Okay.
Yes or no?
Yeah.
Yeah. Now, you go to your formula or basic slide actually. That's why I put those slides here, so that everyone. It doesn't matter whether it is Y or delta. Your S.
Oh, it's just in the
2, 3
calculation.
VL IL.
Yeah. I thought it came from somewhere from the phases very cool.
Basically, go back to the thing. I would ask how what times Q times figure.
Q.
Times what figure?
This Q. Y multiply with 3.
Times it goes.
Okay, this type because of this X value. Because the loss in resistor is the real power, the loss in inductance is the reactive power. Okay?
I just have a question going back to finding the delta system power and reactive power. So this equation was derived from this,
Yeah.
so 3 times by delta
I square R, yeah.
But then why, before you found the value for current for line delta, why did you divide it by 3?
Sorry.
Can you explain why 3 is here?
Okay. I might not be able to explain the whole thing, but basically IP, if you can see here, IL is equal to that. But when you consider IP squared, and then you square the root 3,
Yeah.
and then
Square root 3 power is 3. So you power the whole thing. Square root
Yes or no? Not yet. So you ask me. So this is the line current we calculated, is it?
Yeah.
Now in the power in delta connected circuits, if you look at here, to calculate the power.
Oh, that's only one.
That is
one
phase,
row.
one branch. Yes. So that's
You're thinking about the whole system. That's why.
That's why.
Square root 3.
Yeah.
And then when you square it. Alright, thank
Okay.
you. Yeah.
okay. Let's start again. So, as we have said that there are 4 topics: calculation of power, instantaneous power, root 3 VLIL cos theta, or V3 V phase I phase cos theta. That was the instantaneous power calculation. That was the first part of the lecture. In the second part, we have studied Y and delta connections: phase voltage, phase current, line current. So the third component of this lecture is power factor improvement. That is, I think you have done maybe in some other courses for single phase circuits. So the concept is almost the same. So we will do for 3 phase circuits. So power factor improvement, and this is again another important concept in this course. And you will have, I think, at least 2 tutorials on power factor improvement. And sometimes in the exams also you will be tested on this. So power factor improvement, also known as power factor correction, means reducing the phase difference between voltage and current. So the utilities, they want to maintain a power factor close to unity, but the majority of the loads which have inductance. So the power factor is coming from the angle between resistance and reactance, or reactive power and real power. So for inductive loads, the power factor is going to be low. So that's why most of the utilities, they are required to install some power factor correction equipment within their network to improve the power factor. And the power factor equipment, what it does, it is just most likely a capacitor, and it is providing reactive power to the circuit. So power factor improvement mostly means that we are adding or supplying reactive power to the system. Now, when we study this, so how do we calculate power factor improvement or requirements? The power factor is the ratio between real power and apparent power. And this is actually the power triangle. In the x-axis, we have our reference, real power, then reactive power Q, and apparent power S is actually the resultant of these two. Now, first let's consider the big triangle, bigger one, P and Q1. So our real power is P, our reactive power is Q1, and at that point our apparent power is S1, and our phase angle is phi 1. So this phase angle, this is phi 1. If you take cos phi 1, that will give you the power factor for the first case. Now, maybe that power factor is not good, that is too low, because the relationship between this phi or angle and the cosine is, as the phi angle is higher, the cosine value goes lower, isn't it? Yeah. So if the phi value is high, then cosine value will be low. So that's why what do we want to have in a power system? We want to improve power factor. Improving or making better power factor means reducing your phase angle. So what do we want to do? We have actually power factor Q1. Now for this system, we want to have power factor Q2. It means that we need to have QC, this amount of reactive power, and we want to install a capacitor to get reactive power from that capacitor. Just in the previous problem, when we have calculated real power, our equation was 3I square R, means real power is related with the resistance. Then when we calculated reactive power, the equation was 3I square X. It means reactive power that is related with the capacitor or inductor, that element. Now for this QC, we want to calculate that how much capacitor we need to obtain this amount of reactive power. And if your new reactive power is Q2, then as you can see that your bigger triangle is not exist anymore. When your Q2 changes, your S2 changes, and your angle becomes smaller. And angle becomes smaller means your power factor is higher. So from this power triangle, just what we have said here, that once we have a certain system and we need to do some power factor correction, then we determine that how much power factor we need. For example, in a system you have 0.8 power factor. Now the utilities want you to have 0.9 power factor. So your power factor need to change. Power factor means cos theta will change from 0.8 to 0.9. Cos theta need to change means you need to change your theta. So the new theta is actually that phi 2. If you change your theta, then you can see that your Q2 is changed. Q is changed to Q2 and your S is changed. Now we calculate QC, that how much power factor we need. Then we have actually a formula that to obtain a certain amount of QC, how much capacitor you need. That is the formula for that. In a capacitor C, the reactive power generated, QC equal C omega V square, where omega is the 2 pi f radians per second. So for power factor correction, for QC amount of reactive power, we need to have C amount of capacitance. So this is the way we will calculate how much power factor we need and how much capacitance we will need to have. A Y-connected load, balanced, drawing 25 kVA when you say kVA, what is that? S, apparent power. And the power factor cos theta is 0.85 lagging. And there is a delta connected load drawing 18 kilowatt P at 0.9 power factor lagging. And this Y and delta, they are connected in parallel. The loads are supplied from a balanced Y connected source through a feeder. So the problem here is almost as the same we have solved before. Y connected load, delta connected load, and this combination is supplied from a Y connected source. Calculate the source current. We have done this in the previous problem in some way. And we have done actually separately. We have calculated the real power for Y circuit, reactive power for Y, then calculate the total S, apparent power, then from there we have calculated the line current, source current. In the previous problem, just we have solved, the values of Y and delta were given according to the impedance value. If you remember the previous one, 2 plus J2, 6 plus J6. But here, the same Y and delta connection, but only the ratings are given. Like the whole Y connected circuit, it is a 25 kVA machine. So we can't use those VI equations here to calculate the power. So the approach in this case will be different to calculate the source current. And what else? A delta connected capacitor bank will be connected in parallel to the two loads to improve the overall power factor to 0.5 lagging. So when this Y and delta are connected, for each of these power factor is given. For Y the power factor is 0.85, for delta power factor is 0.9. From there we need to calculate what is the combined total power factor in the first place. Then we have to improve the total power factor to 0.95. And for this, how much capacitance we will need? That's what we have to calculate. So this will be a bit bigger problem, but first half actually we have solved in our previous question. So there are two parallel connected load, one is Y connected and one is delta connected, and their power factor is given. So we have to calculate first the total power factor. Once we get the total power factor, then we have to change that power factor to 0.95. So for load 1, the information is given that it is a 25 kVA, 0.85 power factor lagging. So S is given and cos theta is given. So we have done the calculation that it is 25 and 31.8 degree. That is the value of S in kVA. Now you can express S as P plus JQ, real power, plus J reactive power. for our load 2, that is delta connected, and the information is given 18 kilowatt, 0.9 power factor lagging. That is our load 2. And then we expressed that one as P plus JQ. So we got the real and reactive power for our first load. We got the real and reactive power for our second load. Can anyone tell me what is the real power absorbed by both of the loads, the combination? You just add P1 and P2, isn't it? That's easy. So now we can determine actually the total power consumed, total real power, and total reactive power for these two loads. So the total power consumed by these two loads, or total complex power, that is S1 plus S2. So the total reactive power, total real power consumed by these two loads plus total reactive power consumed by these two loads plus total apparent power. And this is the power factor for the combined load, not power factor, the angle. So from here, this is theta, we can get our cos theta from there. And the line current, this is actually the source current, and the equation is S equal root 3 VLIL. This is the total S, what we got here. Root 3 VL is 415, that is given. So if you compare this problem with the previous problem, they are asking the same line current, and you have calculated the same from the total apparent power, but because here machine rating is given, so you calculate in a different way. And in the previous case, resistance and reactance values were given, so we calculate through voltage and current and all of those. So it was asking for line current, so we have calculated the line current by using all of the formula. It is not that you don't know this formula. You know this, but maybe you don't know when to use this. So if you practice more, maybe you will be familiar that in which case you need to use which equations. All of the equations will be given, but still you need to practice a little bit more. Which one to use at which point. Now it was asking for the line current, so we have done the source current or line current. Now the second problem is delta connected capacitor bank is connected in parallel, and new power factor is 0.9. So after you include the capacitor bank for power factor correction, what is the line current now? We have calculated the line current, it was before. Now what will be the new line current and how much capacitor we need to improve this power factor. So we will address these two issues now. So the power factor, it was 0.837. Now it is saying that it has to be 0.95. From 0.837, you have to bring it to 0.95. How much capacitor we need, or what is the source current? Now if you remember our triangle, in the triangle here, P doesn't change. P remains the same. Because of the change of the angle or power factor angle, Q changes, S changes, and theta changes, but P remains the same. So similarly here, the power factor has to be improved to 0.95. Active power remains the same, as in 39.25 kilowatt here. For the total load, the active power remains the same. The new apparent power will be, if you look at the first line, S new 39.25 divided by 0.95. From where that is coming? That is coming from the power triangle. If you look at the power triangle, here, P is on the x-axis and S is there. So the relationship between S and P is P equal S cos theta. P equal S cos phi. So S will be P divided by cos theta. So that's why we write here S new is P 39.25 divided by cos theta. That is the power factor. So this is P divided by cos theta. That gives us new S, and this S we can represent as P plus JQ. Our real power remains the same, but what is our reactive power? Our reactive power is 12.90 now. And before, it was something else. So we have to calculate that how much reactive power we need to provide more. Again, the line current now, we have calculated line current before by using this formula, but S has been changed. So now root 3 VL is the same, but because of new S, our line current will be different now. That's what we have calculated here in the first step, that how much is the new line current. So the line current has been changed, and we have calculated that from the new S. Secondly, we have been asked to calculate the capacitance value for the reactive power change. So how much reactive power has been changed? Previously it was 21.89, now it is 12.90. So the 8.99 kilovar, 8.99 kilovar capacitance we need now. So because it is close to 9, and that is for a three-phase system, that's why it says that you need 3 kilovar per phase. Because it is a three-phase system, you need 3 kilovar per phase. And the equation to calculate the capacitance required, that we can obtain from this formula. Our QC is 3 per phase capacitance, kilovar reactive power required, C omega is 2 pi f, and V is 450 volt. By using this formula, we can calculate that 57.48 microfarad capacitance is needed, and because this is per phase, at the beginning we divide by 3. So per phase, this is the required capacitance in each of the phases. So the power factor correction is very similar for single phase and three phase. Just we have to consider that for three phase, the capacitance or the reactive power is needed is 3 times more. So we have calculated per phase at the beginning by dividing with 3. So this was about power factor correction. We have to calculate a new Q for reactive power. Then from that reactive power, we use this formula to calculate our capacitance required. Now the fourth topic and the last one, we have 10-15 minutes. That is the power measurement. And I think you have used this before. You use wattmeter to measure power. Wattmeter is used to measure the active power, either in single phase or three phase systems. And what is wattmeter? That is actually a combination of voltmeter and ammeter. And as you know, ammeter is connected in series with a circuit, and voltmeter is connected in parallel with a circuit. And the polarity, sometimes you may see that your wattmeter is giving negative power, especially this is very old analog. Sometimes these days I think we use most of the digital meters. If you see your wattmeter is showing negative power, it means your polarity is not right. So you have to change either voltage polarity or current polarity or the connection. Now, how do we do power measurement in a three-phase, three-wire system? In a single phase, it is easy. You just, because you have 2 wires in a single phase system, you just connect in series ammeter port and in parallel your voltmeter port. But in three-phase, three-wire system, because there are 3 wires at least, or 4 wires, so how do you connect them? So in a three-phase, three-wire system, the active power supplied to 3 load is measured by 2 wattmeter, and it is called 2 wattmeter method. So to calculate three-phase power, in a three-phase circuit, we need to use 2 wattmeter, and the connection, as you can see that our current coil that is connected in series in both of the cases, and voltmeter is measuring the voltage in parallel. Total power equal, if your wattmeter 1 measures P1 and this is P2, the total three-phase power in this circuit will be P1 plus P2. So you use 2 wattmeter, but you get the total power in your three-phase circuit if you connect like this. So you can measure real power in a three-phase, three-wire system like this by connecting 2 wattmeter as shown in here. Now how do you calculate that? If you look at W1, that is measuring your IA, phase A current, and VAB, voltage between phase A and phase B. In which case, the angle between VAB and IA is theta 1. If you look at here, it is measuring your IC, it means again phase current, then VBC or VCB. So that is line to line voltage. Now in case of theta 1, as we have seen before that there is a 30-degree angle between phase voltage and line voltage, or phase current and line current. So your theta 1 will be theta A plus 30 degree, and theta 2 will be theta A minus 30 degree. So as we have said that our total P, total power will be, just if you add them together, P1 plus P2. When you do P1 plus P2 and bring the values of P1 and P2 from here, then you get 2 VLIL cos theta and cos 30 degree. And if you look at here, so that is actually, you have cos A plus B, then plus cos A minus B. And we have used this formula, cos A plus B plus cos A minus B, that is 2 cos A cos B, that becomes theta plus cos 30 degree. And finally you see that the power we measured, that is root 3 VLIL cos theta. That is exactly the power in a three-phase circuit. The real power in a three-phase circuit, whether it is Y connected or delta connected, that is always root 3 VLIL cos theta. So the power you measured by using 2 wattmeter, that is the power consumed in this three-phase circuit. So your wattmeter, 2 wattmeters is measuring the power for your three-phase circuit. That is the proof as well, because 2 wattmeter is measuring this, and this is the total power. Now, how do we calculate power factor angle? To calculate the power factor. So a wattmeter can measure your real power and it can measure your power factor as well. So we have our P1 and P2, and that gives us root 3 VLIL cos theta. Then we calculate P2 minus P1, and if you calculate that, that will give you VLIL sin theta. Then we divide them, and this gives us tan theta over root 3, because this VLIL and this VLIL will cancel out. Sin theta divided by cos theta is tan theta, and just root 3 remains here. So the theta is tan inverse root 3 second wattmeter reading minus first wattmeter reading divided by second wattmeter reading plus first wattmeter reading. So this is to determine the power angle from these 2 wattmeter readings. So 2 formula to remember. First of all, if you are given 2 wattmeters readings, then to obtain the total power, you just add them together. Your total P will be P1 plus P2. And what is the power factor angle? That is theta equal tan inverse root 3 P2 minus P1 divided by P2 plus P1. So if you only have 2 readings of the wattmeters, you know total power, you know power factor. Now let's solve this. 2 wattmeter W1 and W2 are connected, and W1, that is 60 kilowatt, and W2 measures 40 kilowatt. So what is the total power in this circuit? What is the total power consumed in this circuit? 100 kilowatt. That's easy, because whatever 2 wattmeter measures, we just add them together. And the power factor, that is the formula we have seen, that how to calculate the power factor. So this is easy. The total power will be P1 plus P2 or W1 plus W2 measurements, and the power factor we will calculate from tan theta. Root over 3 P2 minus P1 divided by P2 plus P1. So this is easy, this is straightforward, but because this wattmeter readings and calculations, this is I think something specific to this course. So you have to learn and solve problems a little bit on this issue. In tutorial I think you have to. So just you want to solve another problem in this. 2 wattmeter, this is another problem. The 2 wattmeter method is used to measure the power drawn by a balanced load connected ABC terminals, 50 Hz, 415 volt supply. The current coil of the two wattmeters are connected in A and C if the load is Y connected with impedance of this, determine the ammeter reading. So what it is asking actually, because you have connected two wattmeters, and you know in wattmeter the current coil is always connected with one of the phase currents. So it is asking that what is the ammeter reading. It is asking actually the line current. Your line current will be your ammeter reading. Then what is the rating in 2 wattmeters and what is the total power consumed by the load. So with the information given here, the ammeter reading, that is actually just the line current or phase. It is the same as phase current for Y connected circuits. The line to line voltage is given 415. We divide with √3 to make that into phase voltage, and we divide with the impedance to get the phase current. Then the readings of the 2 wattmeter. We have seen the formula for P1 and P2. So what are those? Your P1 equation is phase to phase voltage, line to line voltage, phase current, cos theta. So line voltage